In the last lecture, we calculated that in the absence of the atmosphere, the Earth's surface temperature would average about minus 18 degrees centigrade, which can be compared to the observed temperature of about plus 15 degrees C. How are we to understand that difference? That difference is owing to the greenhouse effect. The greenhouse effect has a long and illustrious history. Arguably, the first scientist to understand this was Jean-Baptiste Joseph Fourier, who lived from 1768 to 1830. He was the first to show that gases within the atmosphere absorb infrared radiation trying to leave the planet, and we radiate some of that energy down to the surface. But quantitatively, the first real strides forward were made by the Irish physicist John Tyndall, who lived from 1820 to 1893. At the bottom of this diagram, we see a picture of John Tyndall's apparatus for measuring the transmission of radiation through air. Tyndall made some remarkable discoveries. Perhaps the most surprising is that molecular oxygen and nitrogen, which together comprise about 97% of the mass of the atmosphere, are transparent to solar and infrared radiation. The fundamental reason why this is so is the simplicity of the structure of molecular oxygen and nitrogen. Basically, you have two atoms of gas which have a very limited number of degrees of freedom for interacting with radiation. If that is all we had in the atmosphere, if we only had oxygen and nitrogen, then the equation we developed in the last video would be correct, and we would have a surface temperature of about 255 Kelvin or 0 degrees Fahrenheit. Obviously, we'd have a very different planet. Tyndall discovered that certain trace gases interact strongly with radiation. Principally, these gases are water vapor, H2O, which we saw before, is variable, but on average comprises about 0.25% of the atmosphere. Carbon dioxide, whose concentrations are measured in hundreds of parts per million, and methane. Fundamentally, the reason why these gases interact more strongly with radiation is that they are more complex in their structure. We'll be talking about this later in the course. They have far more degrees of freedom in interacting with radiation. Together with clouds, which are comprised of condensed water and which also interact strongly with radiation, they cause something called the greenhouse effect, which renders the surface temperature much higher, about 288 degrees Kelvin, or about 60 degrees Fahrenheit. So let's review Tyndall's essential results. Oxygen and nitrogen, although they make up close to 98% of the atmosphere, are almost entirely transparent to solar and terrestrial radiation. But water vapor, carbon dioxide, nitrous oxide, and a handful of other trace gases make the lower atmosphere nearly opaque to infrared radiation, though still largely transparent to solar radiation. But clouds have a strong effect on radiation at all wavelengths. Let's look at this a bit more quantitatively. Here we have a diagram on whose x-axis is the wavelength of the radiation, varying from 0.2 microns to 70 microns. Now let's focus on the top of this graph first. Look at this red line. This is the so-called Planck blackbody function for the mean emission temperature of the sun. This is basically showing the amount of radiation incident on the Earth at the top of the atmosphere as a function of wavelength. The curves that you see over on the right-hand side of this diagram are the Planck functions for the Earth's temperature, ranging from 210 degrees, over here this black line, to 310 degrees, this purple line. Now you notice that the Planck functions for the sun and for the Earth have hardly any overlap here. So it's meaningful to talk about solar and terrestrial radiation as two entirely separate streams of radiation. Underneath these curves, you see the colored regions here with notches. This shows the actual amount of radiation received at the surface. And by comparing this to the Planck function, one can get some idea of how much of this radiation has been absorbed on the way. You'll notice that the very shortest wavelengths, which are the ultraviolet part of the solar spectrum, are almost entirely absorbed. It turns out to be by ozone. We'll see that in a minute. These various notches down here represent collections of absorption bands, mostly, it turns out, by water vapor, that also absorb some of the solar radiation. I should mention at this point that in this diagram we have not included the effects of clouds. Let's look at the diagram over here on the right. This portion of the diagram, the blue shading, shows how much of the radiation emitted by the surface is actually transmitted through the top of the atmosphere. And the net, only about 15 to 30% of it is. Virtually all the near-infrared and far-infrared parts of the terrestrial spectrum have been absorbed. This is the greenhouse effect in action. Relatively few of the photons that leave the surface of the Earth make it out to space. Now, this middle diagram down here shows the total amount of absorption and scattering going on in the atmosphere. Basically, it's the difference between the Planck functions you see here and the actual transmittances. So you see that once again over here in the ultraviolet part of the spectrum, almost all of the solar radiation is absorbed, and here are collections of absorption bands in the relatively long wave part of the solar spectrum. Notice also that there is this band here where almost all the solar radiation gets through. This is in the visible part of the spectrum. It's probably not an accident that our eyes have evolved to see in this part of the spectrum where very little light is absorbed by the atmosphere. Now, when you get over into the infrared part of the spectrum, the terrestrial part, notice that in the near and far infrared regions, there's almost total absorption. Finally, at the bottom of this diagram, we can see what it is in the atmosphere that's doing this absorption and scattering. Let's begin with the scattering. This really only seriously affects solar radiation at the very short wavelength end. A lot of the short wavelength blue and ultraviolet light is scattered. This is in fact why the sky is blue. Blue light in the visible is preferentially scattered compared to the longer wavelengths. And the scattering at terrestrial wavelengths is almost entirely absent. The various bars above this show which constituents of the atmosphere are actually absorbing solar and terrestrial radiation. Nitrous oxide has some absorption bands, mostly in the infrared. Methane has a prominent absorption band in the terrestrial part of the spectrum. Oxygen and ozone together have a minor absorption bands until you get out into the ultraviolet. This is ozone principally in the stratosphere that, fortunately for us, is taking out most of the ultraviolet radiation, which is highly damaging to life forms on the surface. This band here shows absorption by carbon dioxide, quite a few bands in the terrestrial part of the spectrum, and finally by water vapor, a great deal of the absorption of both solar and infrared radiation that occurs in the atmosphere is by water vapor. Water vapor is far and away the most important greenhouse gas.